Hello everyone, welcome to a video about atomic structure, emissions and energy levels. I've collated a few different sets of learning intentions and success criteria into this probably long-ish introduction to this section. I suspect that some of this may be revision from other sciences, it may not be, but regardless we'll cover it, so if it is new information it will all be here. I just figured it would be best to collate it rather than into one, I guess, a bit longer video rather than having lots of little short videos that are cutting off at random points, so it felt better to just put it all together. The first learning intention that we'll look at is that a continuous spectrum contains a continuous range of frequencies, and that solid, liquid, or dense gaseous objects radiate a continuous spectrum which may extend into or beyond the visible region. This is known as incandescence, and the frequency distribution and hence dominant colour depends on the temperature of an object. In stage 2 physics, you need to be able to describe the changes in the spectrum of a filament globe as the temperature of the filament increases. So I'll just recap electromagnetic radiation. Just to remind you, all solids, liquids and gases that are above 0 degrees Kelvin, so above absolute zero, emit electromagnetic radiation. The spectrum, peak wavelength or frequency and intensity is all or are all proportional to the temperature. The peak wavelength is the wavelength at which the intensity per wavelength interval is largest, and this is always going to be the dominant colour that's emitted. So if you've got a peak wavelength at your green wavelengths, then you're going to view the object that's emitting the radiation as a green object, or whatever is the peak wavelength, whatever colour corresponds to the peak wavelength. The intensity is the power output per unit area at each wavelength interval, and this is sometimes called the spectral power density. The reason that temperature determines the spectrum, peak wavelength and intensity is because the vibrational kinetic energy of the atoms that make up an object increased as the temperature increases. A continuous spectrum is the continuous range of electromagnetic frequencies that are emitted by solids, liquids or dense gases with a temperature above absolute zero. And the reason that this is continuous, so it's not discrete like individual frequencies, the reason that this is continuous is because there's a continuous range of oscillating frequencies of the vibrating particles, so the vibrating atoms and molecules. So the frequency of any given atom in a collection of like billions of atoms or even more that make up an object or make up a gas or a liquid is going to result in a spectrum of frequencies that are emitted by whatever object or substance we're talking about. This continuous spectrum is solely dependent on the temperature in the object, and it doesn't provide any information about the atomic composition of an object, so it's purely just based on temperature. You can't glean any extra information about the atomic constituents of an object. This particular image in the top corner here is the emission spectra of a fluorescent lamp. So you can see that it is continuous, but there are certain peak frequencies. So here in blue, then there's a little one just at violet, and the green is kind of jumps up as well. And then there's a general like increase, I suppose, like in general for the yellow, red, and orange wavelengths as compared with the general blue and violets and shorter wavelengths, apart from those like individual peaks. So this image or graph here is the wavelength distribution of an object at different temperatures. So it's showing the intensity or spectral power density or power output per unit area at each wavelength interval. It's a graph of that versus the wavelength of electromagnetic radiation that's being emitted. So you can see that as the temperature increases, so I've got 3000 Kelvin down the bottom and 6000 Kelvin up the top in red, you can see that as the temperature increases, the intensity or spectral power density increases. So the peak for 6000 Kelvin is much higher and incidentally earlier than the peak for the object at 3000 Kelvin. So as you can imagine, as the temperature of a filament globe increases, the spectrum that it emits is also going to change. So because the peak wavelength is becoming shorter and shorter as the temperature increases, the observed color or observed wavelength is going to change as the temperature increases. So now we're going to look at emission spectra. So I'll just read the learning intention and success criteria. So atoms can be raised to excited states by heating or by bombardment with light particles such as electrons. The heated vapor of a pure element emits light of discrete frequencies, resulting in a line emission spectrum when the light is viewed with a spectrometer. In stage 2 physics, you need to be able to describe the general characteristics of the line emission spectra of elements. You also need to explain how the uniqueness of the spectra of elements can be used to identify the presence of an element. And you need to be able to explain the production of characteristic X-rays in an X-ray tube. So reflecting back a little bit to our X-ray production video. So emission spectra, low density gases that are energized either by light, heat or electricity emit discrete wavelengths which form a line emission spectrum. So up the top we've got a continuous spectrum which just shows the entire visible spectrum from red light all the way through to violet light. With an emission spectrum, you're only going to get certain segments or certain discrete frequencies that are included in your spectrum, and that's going to be unique depending on the type of atom or the element that you're specifically looking at. In the production of an emission spectrum, electrons will absorb energy, they become excited, and then they'll release this energy shortly afterwards in the form of a photon, and it's the frequency of the released photons that correspond with the lines in the emission spectrum. A line emission spectrum is a discrete spectrum containing sharp coloured spectral lines. So each of these lines here is a spectral line, and they correspond with a specific wavelength emitted by a low density gas that has been excited and is releasing these photons of energy. These lines are detected by a spectrometer or a spectroscope, and this is like a telescopy kind of instrument that when you look through it separates light into its constituent wavelengths, so the wavelengths that make up a particular light emission. Elements or compounds will emit unique line emission spectrums, And so these spectrums can be used to identify for the presence of these elements or the presence of these compounds in unknown samples. This is useful in chemical analysis of things like soils, minerals, and air pollutants. It also has application in investigating the atmospheres of given planets, moons, and stars. So now we'll look at energy transitions. So the energy states of an atom depend on the internal motion of the particles in an atom. So when an atom is in a ground state, this means that all of its electrons are in the lowest possible energy state. So there's no excess energy. In an excited state, an atom's electrons are in a higher energy state, and this higher energy state corresponds with a transient, so for a few nanoseconds, a transition to an electron orbit that is further away from the nucleus before quickly returning back to the ground state. So excited atoms will have electrons that will jump up from their initial or original energy state or original orbit to a higher orbit that's further away from the nucleus before jumping back down to their original orbit, because when they're further away from the nucleus, they're a bit less stable. Energy state transitions, so from ground state to excited state or between two higher states, these result from the emission or absorption of energy that is equal to the difference between the two states. So this can occur via photon emission. So if an electron emits a photon, so it's getting rid of energy, that must mean that it's moving to a lower energy state because it has less energy than it had before. If a photon is absorbed, this means that an electron is moving to a higher energy state. So it's going from a lower energy state, absorbing a photon, and then jumping up to a higher energy level. So if something is moving from ground state to its excited state back to its ground state, it's absorbing a photon and then emitting a photon. So absorbing, going up to the higher state, emitting, going back down to ground state. A third way of transitioning is by collisional excitation, and this is when energy is absorbed due to a collision with another particle. So, for example, an external electron colliding with an inner shell electron, which we touched on when we were talking about X-rays 1 or 2 videos ago. So in collisional excitation, often the inner shell electron completely disappears from the atom. So what has happened is so much energy has been transferred to this electron that it gains enough energy to actually completely leave the atom. So it's moved to a higher energy state, and that energy state just happens to be, I suppose, an infinite state relative to the atom, so it's completely left. There's a good diagram of the 3 types of energy state transitions on page 376 of the workbook. So I think sometimes it can be best to look at images and diagrams of these things to kind of solidify your understanding. So the emission spectrum of an atom or an element is the spectrum observed when low density gases emit photons equal to the energy difference between excited states. So we've got an electron, or we've got an atom that's in an excited state here. It's emitted a photon over here, and now it's gone, the electron has gone back to its original shell, and the atom is now in a ground state. So the emission spectrum is the spectrum observed when these photons are emitted from atoms that are excited, or if they're emitted from electrons that are in higher energy states than they usually would be. There are various excited states for each atom or molecule, and so a wide array of photon emission is possible. The discrete wavelengths of photons emitted by valence electrons form the spectral lines of an emission spectrum. So these discrete lines here correspond, or these discrete spectral lines correspond with the discrete photons emitted by the electrons that have been raised up to higher energy levels, and then which have released photons to then come back down to their normal energy level or their normal electron shell. This graphic here highlights that there's different jumps that can be made between different energy levels, and these different jumps are responsible for the different photons that might be emitted once these electrons are emitting this extra energy. Emission spectrums are also sometimes called optical spectrums, so just a heads up if you do come across that language used instead. And that's just because the wavelengths correspond with visible regions in the electromagnetic spectrum. There's also some good diagrams of this on page 377 of your workbook, so I'd suggest having a look at this as well. So now we'll quickly revisit characteristic X-rays, which we touched on in a previous video. Photons are also emitted when outer shell electrons transition to inner shell electron vacancies. So electrons don't necessarily have to jump up to a higher energy level to then jump back down. If there's a vacancy that appears in a lower level, then a higher level electron can fill that vacancy. So with characteristic X-rays, they're produced when high-speed electrons, so external electrons, are fired into an atom and they collide with the inner shell electrons, and this displaces that inner shell electron. Because there's a vacancy, that inner shell vacancy is filled with an outer shell electron, and this can be any outer shell electron. So there could be multiple characteristic, and in fact there usually are, multiple characteristic X-rays, because we don't know if an electron from the second shell or the third shell or beyond is going to jump down and fill that vacancy in the inner shell. There's a large energy difference between inner shell and outer shell electrons. So the photons that are produced have X-ray wavelength and frequency. So they have a high frequency and a short wavelength, because a high frequency corresponds with high energy. In our diagram here, we're starting off with a neutral atom that has a internal electron displaced either by an ion or electron beam, and then that vacancy is then filled by an external electron that jumps down to where that vacancy is, and because it's jumping down to a lower energy level, it gets rid of some of its own energy that it has from being in a higher vacancy shell, and that is emitted as an X-ray. So now we're going to look at another set of learning intentions and success criteria. So the presence of discrete frequencies in the spectra of atoms is evidence for the existence of different states in atoms. The states have their own specific energies. The different energies can be represented on an energy level diagram, and when an electron makes a transition from a higher energy state to a lower energy state in an atom, the energy of the atom decreases and can be released as a photon. The energy of the emitted photon is given by the difference in the electron energy levels of the atom, and and an atom is in its ground state when its electrons have their lowest energy. If an electron is in any of the higher energy states, the atom is said to be in an excited state. So a bit of a mouthful there. Hopefully some of this is recapping stuff that you already know. But if not, no worries at all, we'll cover it in this video. So in stage 2 physics, you need to be able to explain how the presence of discrete frequencies in line emission spectra provides evidence for the existence of states with discrete energies in atoms. You also need to be able to solve problems involving emitted photons and electron energy levels of atoms. You need to be able to draw electron energy level diagrams to represent the energies of different states in atoms. And given an electron energy level diagram, you need to be able to calculate the frequencies and wavelengths of the lines corresponding to specified transitions. Energy level transitions. So Bohr hypothesized that each atom has a discrete set of energy levels, and this is supported by line emission spectra. This hypothesis suggests that the internal energy of an atom corresponds with these discrete energy levels, but not with energy that would be in between these levels. The energy levels are circular electron orbits of permitted radii, and the emission spectrum is a result of photons with different energy and hence different wavelengths being emitted when an electron transitions from a higher to a lower state. So when an electron is emitting a photon, it's getting rid of some energy and it's moving down to a lower energy state. The energy difference between the initial and final levels is going to be equal to the energy of the initial level, which is going to be the higher energy level, minus the energy level of the final level, which will be the level that's closer to the nucleus. And this will be equal to the energy of the emitted photon, which is Planck's constant multiplied by the frequency of the photon. So the energy difference is also equal to the energy of the emitted photon. And this is an example of the law of conservation of energy. So as an example, the frequency of a photon of light emitted from a sodium vapor lamp is 5.1 by 10 to the 14 Hertz. What is the energy of the photon in joules and in electron volts? So to do this, we'll just use the rule that we just looked at. So initial energy minus the final energy is equal to Planck's constant multiplied by the frequency. We know that the frequency is 5.1 by 10 to the 14 Hertz, and we know that Planck's constant is going to be equal to 6.63 by 10 to the negative 34. So our energy of the photon is going to be 6.63 by 10 to the negative 4 multiplied by 5.1 by 10 to the 14 Hertz. And then this is going to be equal to 3.4 by 10 to the negative 19 joules. If we then wanted to convert this to electron volts, so we've found the energy in joules, we just need to find it in electron volts now. We just have to divide 3.4 by 10 to the negative 19 by 1.6 by 10 to the negative 19, and that's going to give us 2.125 electron volts. So in electron volts, the answer is 2.125. In joules, the answer is 3 by 10 to the negative 19. Let's now look at energy level diagrams. So we've got the energy level diagram for hydrogen on the right. These identify the known energy levels of valence electrons in atoms. The lowest level, so n equals 1, corresponds with the ground state, so the lowest level of valence electrons. In hydrogen, the ground state is at negative 13.6 electron volts, so that's the potential energy of the electron. So that is the energy that the electron would have to gain to be fully released from the hydrogen atom, so it's like pretty stuck in there. Excited states for electrons correspond with levels above the ground state. So if an electron from the ground state leaves the ground state and moves up to N2, N3, N4, etc., then that would mean that the atom is excited, or the hydrogen atom is excited. The highest level, so when the energy is equal to 0 and when n is equal to infinity, this is the ionization limit, so when the electron is actually separated from the nucleus. So the atom is ionized, so it's lost an electron. And the continuum, which isn't shown in this picture, but it's usually like a shaded in section called the continuum. This is above the ionization limit, and it's when the electron is no longer bound to the atom, so it has a continuous range of energy because it's free from the atom, so it's free to move around and do whatever it wants. So we've got an example here. Calculate the frequency of a photon emitted from an electron in a hydrogen atom transitioning from N4 to N2. So we'll be looking at these values here for energy. To do this, we'll use our rule. So initial energy minus final energy is going to be equal to Planck's constant multiplied by frequency. And then if we rearrange this, we'll get frequency is equal to the initial energy minus the final energy divided by Planck's constant. Now, because these values here are given to us in electron volts, what I'm going to do is multiply, I'm going to put this in brackets and multiply the top by 1.6 by 10 to the negative 19, and this will then convert these values here into joules. So it's going to match up with my Planck's constant, which I'm going to do in joules. So we'll end up with the initial energy, which is negative 0.85 electron volts, and then minus negative 3.4 electron volts, and then hopefully I can squeeze this in, 1.6 by 10 to the negative 19, so multiplying by and the charge on an electron, and then dividing everything by 6.63 by 10 to the negative 34. If you were to then pop everything into your calculator, so you'd end up with 0.85 plus 3.4, and then whatever that is multiplied by 1.6 by 10 to the negative 19, and then dividing that whole thing by 6.63 by 10 to the negative 34, you'll end up with a frequency of 6.15 times by 10 to the 14 hertz. Sorry if you can hear some weird sounds, just hanging out with the dog. So yeah, your frequency for the emitted photon is going to be 6.15 by 10 to the 14 hertz. So that's if an electron in hydrogen is transitioning from N4 to N2. The last set of learning intentions and success criteria for these videos are: the line emission spectrum of atomic hydrogen consists of several series of lines, and the ionization energy of hydrogen is the minimum energy required to remove the electron from hydrogen in its ground state. So for stage 2 physics, you need to be able to draw on an electron energy level diagram of hydrogen transitions corresponding to each of the series terminating at the 3 lowest energy levels. You need to be able to relate the magnitude of the transitions of an electron energy level diagram to the region in an electromagnetic spectrum of emitted photons. So this could be ultraviolet, visible, or infrared sections of the electromagnetic spectrum. And using an energy level diagram, you need to determine the ionization energy, either in joules or electron volts, of hydrogen. So for the hydrogen emission spectrum, the spectral series in this correspond with electrons transitioning between energy levels of the atom. There are 3 different series corresponding with different ranges or wavelength ranges that you need to know. These are the Lyman, Balmer, and Paschen series. Lyman corresponds with UV, the UV range. So if we've got our frequency graph here, the Lyman series is over here. So it's got the highest frequency photons, and these transitions correspond, or these photons are emitted whenever any outer shell electrons transition to the innermost electron shell. So transitioning to that n equals 1 level. The Balmer series are visible, and these series, or these photons, corresponds with all outer shell electrons transitioning to the second innermost electron shell. So these photons are going to have lower energy, so a lower frequency than the Lyman series, because anything transitioning from an outer electron shell to the second innermost shell is going to have a lesser energy than something transitioning from outer electron shells to the innermost electron shell, because the difference in energy is going to be greater. So the Balmer series correspond with visible light, and anything transitioning to the second innermost shell from further out. And finally, the Paschen series corresponds with infrared photons, or infrared frequencies. So the wavelengths will be long and the frequencies will be low. So the energy is lower than Balmer and obviously lower than Lyman. And this series corresponds with anything transitioning to the third innermost shell. So like the second, anything transitioning from the outer shells to a second innermost shell is going to have less energy than anything from the outside transitioning to the first shell. Anything transitioning from outer shells to the third innermost shell is going to have less energy again, and therefore a lower frequency. So this slide is just showing a few different ways of representing this. On the right, we've got an energy level diagram. So the Lyman series is corresponding to all of the outer shell electrons moving down to the first electron shell. So it doesn't matter if it's moving from the second innermost, third innermost, fourth innermost, etc. If an electron is moving to the first electron shell, or the n equals 1 level, then it's going to be part of the Lyman series in hydrogen. For the Balmer series, it's anything moving down to the second innermost shell, and then the Paschen series is anything moving to the third innermost shell. There's also the bracket series and beyond, but we're just focusing on these 3, so Lyman, Balmer, and Paschen. on your right is just another way of representing this, but it's just using like actual concentric electron shells, and you've got the wavelength of each photon listed next to each electron jump, I suppose. So Lyman up the top, so the highest frequency, highest energy, Balmer series, visible light in the middle, middle of the range frequencies and wavelengths, and then Passion series, which are the infrared and the lowest frequencies and longest wavelengths. And lastly, we'll just take a look at the ionization energy. This is the minimum energy required to remove an electron from an atom in its ground state, and it's equal to the magnitude of the n equals 1 energy level. And this makes sense because an electron in the ground state, so at n equals 1, it's going to have the lowest energy, so it's going to require the most energy to leave the atom or ionize the atom. So it's going to be equal to the energy or the magnitude of the energy of that particular level, so n equals 1 level. An atom is ionized when sufficient energy is transferred to remove a valence electron from the lowest energy level. So getting rid of that valence electron from its lowest energy level is going to ionize the atom. And on page 388 of your workbook, you've got the ionization energies of several chemical elements listed.